So that will show up as 2 videos today, right? Since we broke the session, it will appear as 2 videos. Okay.
Yes. Okay.
So is this one clear to you?
Yes.
That the sending machine establishes a connection with the receiving machine, and they exchange parameters which or parameter of or common capabilities so that they can smoothly send the data, right? So once they do this,
Yes.
What is the parameter meaning here? Like the reply
come again, please.
parameter.
No, parameters is
Like what is
actually,
the parameter meaning here?
let's say the first thing is making sure that that the machine B is actually active on the network,
Yes.
right? Would there be any point in him sending data if B is not on? The machine B is not on, is not reachable.
Mhm.
That is one of the things that happens when I send a SYN and I receive a SYN ACK. That means B is there, active, and is ready to accept my communication, right?
Uh-huh.
Then when I say parameters, the primary parameter can be the bandwidth at which both of them are able to capable of sending and receiving.
Uh-huh.
Is that okay?
Uh-huh. Yes.
All right. Now there are a few more things which we will discuss over the next differences,
Hmm.
right? But right now, suffice to say that TCP established some sort of a connection before actually starting the data transfer,
Hmm.
right?
Yes.
And the initial function is established by the three-way handshake. Because you might face a question somewhere along the line as to how does TCP do its connection-oriented stuff, right?
Hmm.
So you can the simple answer would be using a three-way handshake.
Hmm.
Now, if they go ahead and ask you what is a three-way handshake, then you can basically say that the negotiation that happened before the data transfer in terms vis-a-vis a SYN sent by the sending machine or a synchronization request with the receiver sending back a synchronization of its own or his own details along with an acknowledgement for the first synchronization request, and machine A, the sender sends back a final acknowledgement before starting the data transfer.
Hmm. Yes.
Yeah. See, at a CCNA level, they will not go that deep into it anyway, right? But I'm going this far into it because since we are taking time out to do this, might as well go all the way, right?
Yes.
Okay. So it establishes and then the parameters are negotiated, and then the data is transferred, which is why TCP is called
Connection oriented.
a connection oriented. He establishes a session, a connection before he actually starts the transmission. Now UDP on the other hand has got no such overheads,
Hmm.
right? UDP would be like what? See, think about the difference between sending a postcard and sending a registered mail. What would be the difference?
Mm, on the standard postcard, you don't know that the receiver get or not, but on
Exactly.
the register, you get know that the person who going to receive, he get the mail.
Exactly. Right? So UDP is what? UDP is like a postcard. The UDP
Yes.
protocol, when it is sending some data, he doesn't really care whether the mother machine is active, whether he's received it or not. None of that matters to him. UDP will just put the proper address on it and just throw it out onto the network. So the receiver gets it, doesn't get it, UDP doesn't care. But TCP, on the other hand, make sure that the other machine is active before I actually send some data across. Clear?
Yes.
Let's talk about the second difference.
So what is the example of UDP? What do you think, sir?
We'll come to that. That will be the last question in this session. And the question is supposed to come to you,
Oh, okay.
come from you. Because once we go through all this, the differences, you're going to ask me one specific question. So I'll wait for that question towards the end. So the second thing we say about TCP is that TCP is a reliable protocol, right?
Yes.
and UDP is unreliable. Now again, the way TCP does that is you have your machine A, you have your machine B. If it is TCP that is doing its job there, machine A, let's say, sends a few packets here, right? Let's say 4 packets have been sent. Now TCP would expect a acknowledgement for machine B to say, okay, fine, man, I got the 4 packets, go on sending the balance. Now, what happens if there is no acknowledgement?
It not get any means if the A not get any response from the B, the A not going to send any package or
No,
anything.
A would actually retransmit the data.
Yeah.
Correct. TCP has a habit of
Okay.
retransmitting.
Yes.
Say in this courses, let's say the first 4 packets got an acknowledgement, the second 4 packets got an acknowledgement, but the third set of 4 did not get an acknowledgement. So yes, I'm not saying that A is going to wait for the acknowledgement. A is going to continuously send it, and he is going to keep track of the acknowledgements. And after this, he is going to continue sending the next set. But since he did not get an acknowledgement this particular batch, he would retransmit again at that point of time.
Oh,
Got it? That's why it's
okay.
called a reliable protocol. Meaning, if I am sending something to a machine, TCP makes sure that machine B has received the complete content. Whatever is missing, he would retransmit until he gets a acknowledgement from me.
Okay.
UDP, again on the other side, nothing. It does not have a mechanism of acknowledgement. UDP is what we call the Hail Mary protocol. I mean, what do you guys do before you go into an exam? Back in college days, what was a common thing everybody did before they walked into an exam hall?
Make sure they are ready.
Who is ready?
They are ready for the exam. The
you mean
student.
you mean they are ready to give you an exam? That's not what I'm talking about. I mean, I'm not talking about today where we are all a little more sensible, but I don't think back in college days we were all that sensible, right?
Yeah.
I definitely was nowhere close to being sensible. That much I'm sure. I remember we used to have this habit of sending a short prayer upstairs before walking into the exam hall or before starting the exam.
Yes.
Yeah, and are we sure that whoever he or she up there is actually bothering to listen to you? Awake, might be busy with other things. Yeah, so you are sending a prayer hoping that he or she will hear you and he will, okay, the poor chap is going to write his exam, let me give him a few easy questions. I don't think that's how it works, right?
Yes.
So UDP is like that. You are sending it out and hoping that he receives it. Since there is no way to make sure, since there is no acknowledgement mechanism built into that. All right, clear on that?
Yes.
All right. The next functionality here would be what we call sequencing. What is a sequence?
Uh,
A series, right?
it's a pet.
Something in an
Yes.
order.
Yes.
And there's an order to things, right? So,
Yes.
if you look at the structure of the internet is built up of multiple connections, right? To reach any point, you can have multiple paths or multiple ways of going to it. I mean, it's an interconnected network, right? So, I have a machine here and I have a machine here. This guy is trying to send some data to this machine, right? Now, it's just like riding from one point to another. Depending on the traffic, you might take a different road, right? If there's heavy traffic on one road, you might take a side road.
Yes.
Similarly, when I'm sending a bunch of data over to this machine, this router here could decide that, okay, I'm sending some packets this way, but then this is begin to look overcrowded, so I am going to send a couple of packets this way and maybe a couple of packets that way, right? So when ultimately all
Yes.
these packets reach here, there is no guarantee that they reach in the same order, because this might be a longer route, it might be loaded, so the packets are moving slower, right? So there's no guarantee that
Yes.
the packets which left will reach in the right order. This is where TCP has a habit of sequencing them. When he sends it, he is going to do that, right? So once TCP at the other end receives it, even if it comes in the wrong order, based on the sequence numbers, can he put it back in the right order,
Yeah.
right? Now again, sequencing is one of the things. Remember, I think Faiz asked me what are the parameters in synchronization.
Mhm.
This is one of it. They say, okay, I am going to start numbering my packets from say 33,500 or 500, right? So now machine B knows that the first packet will be labeled 33,500, second packet would be 33,501, 502, and so forth, so on and so forth. So this is one of the parameters. Sequence numbers are one of the parameters they exchange. So both the machines will have their own order of sequence numbers, while they can each keep track of it on the other side, right? Now UDP on the other hand, nope, nothing. He just sends it. If it comes in the right order, God bless you. If it doesn't, I have no idea. That's what UDP's attitude to it. See, because he doesn't care whether the other machine is alive or not, right?
Yes.
There's no chance of him caring whether you got it or not. He doesn't even care if you're alive
Yeah.
or not, right? The next one would be what we call windowing. Now, think about it this way, right? Acknowledgements are all good, right? Reliability is a great factor. Getting acknowledgements are all good. But what if there's an acknowledgement for every packet of data? That would be like, see, normally what do? I speak a few sentences and then ask you, is that clear to you, right?
Yes.
What if I expect you to say that yes after every word I say? Wouldn't make much sense, right?
Yes.
Because when you're transferring, let's say, 1 GB file between two machines, right? At a rough calculation, it is almost 800,000 packets, right?
Yes.
So if I expect machine B to acknowledge every one of them, then acknowledgements would itself eat a major amount of bandwidth available, right? For every packet, if the machine B is sending a acknowledged, 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 that doesn't make much sense, right?
Yes.
So basically,
Yes.
windowing would mean, again, Files for you, during the initial negotiation phase, they define or negotiate a window size. So let's say machine A says, all right, I am going to send, and in today's bandwidth availability, the window size is anywhere between 3,000 to 5,000 packets, right? So what they're saying is, listen, I will send you 3,000 packets at one go, and you can give me a single acknowledgement for that. So if I don't get an acknowledgement, I'll send retransmit the whole window all over again,
Yes.
thereby reducing the number of acknowledgements on the network. Got it? Now, TCP along with windowing has got to have one more feature called bandwidth optimization. When you're downloading
Sir,
something
I'm
from,
really sorry, but I did not understand windowing. I'm really sorry to say this.
no problems at all. See, what I'm saying is that what does a window size mean? There's a certain size to something, right?
Window?
Window, a window,
Hmm.
right?
Yeah.
What they're trying to negotiate here is, if machine A expects an acknowledgement for every packet that he is sending, right? So if
Uh-huh.
machine A is sending 1,000 packets, and he expects B to acknowledge every one of them, that would mean 1,000 acknowledgement packets coming back on the network, right?
Yes.
That would mean that much bandwidth is being wasted. So even acknowledgements take bandwidth, right? And bandwidth is precious. You don't have that much of a bandwidth available on the internet,
Mm-hmm.
right? So what they do is before they during the initial handshake phase itself, they agree on a common window size, right? So for example, machine A will say that don't send me an acknowledgement after every packet. You send me an acknowledgement after
Mm-hmm.
my first 3,000 packets.
Mm-hmm.
One acknowledgement for 3,000 packets. Let's see how that goes. Let's say they have agreed on a window size of, since I'm not going to draw 3,000 lines here, let's say they agree on a window size of 2, right? That would be funny, right? If I try to draw 3,000 packets here, 3,000 lines here. So let's say machine A, after they agreed on a window size of 2, machine A sends packets 1 and 2, right? Since sequencing is also involved. And I'm not saying that A is going to wait. He is going to go ahead and send packets 3 and 4. But meanwhile, he would expect a acknowledgement here because two two packets is the window size they agreed on, which means B has to acknowledge after every 2 packets. And here he would continue on with 5 and 6. Meanwhile, he would be expecting an acknowledgement here saying that yes, I got 3 and 4, kindly send 5 and 6. So this number here, the number of packets after
Mm-hmm.
which I would expect an acknowledgement, is called the window size, and not an acknowledgement after every packet.
Mm-hmm.
Is that better, Faiz?
Yes.
Now, when we talk about bandwidth optimization, and that is actually linked to windowing, when you download something from the internet, what do you see your download
Mm-hmm.
speed as? As a flat line or something like that? What is it normally?
Yeah, something like the down one, up and down.
Correct. Now, what do you think is happening there?
Mm-hmm.
TCP,
Mm,
once they agree on a window size of, let's say, 2, right? And he sends 2 packets, he get a proper acknowledgement. He sends 2 again, he gets a proper acknowledgement. TCP will try. What does that mean? I mean, when I'm sending 2 packets and I'm getting a proper acknowledgement, that means there is adequate bandwidth for sending 2 packets, right?
yes,
Getting the acknowledgements properly means that there is no packet drop. What I'm sending, he is getting it. That's why I'm getting proper acknowledgements that he's received them, right?
yes,
Okay. So then TCP, what it tries to do, the sender automatically tries to push the window size. So instead of sending 2, he might send 4. He might increase the window size to 4, right? And if he gets an acknowledgement a couple of times, what does that mean? Okay, there is more than enough bandwidth for sending 4 packets at a time.
Mm-hmm.
And he keeps increasing. And he's not going to 2 and 4 packets. Today's networks, they always start at somewhere around the 3K range and push it up all the way to 8 to 12. Now, that is the spike you are seeing. When TCP increases that, that is where you see this going up, the bandwidth going up, right? But at some
yes,
point of time, the network is not able to take that many packets at a time, right? So maybe he reached the 12,000 packets range for a single window, which means what? It does not reach the other machine. And if it does not reach the other machine, there will not be an acknowledgement, right?
yes,
In which case, so suppose he started out with, like, say, 2, then went to 5, then went to 8, then went to 12. So all along here, acknowledgements were coming, right?
yes,
But here, there was no acknowledgement, which means the network is not capable of taking that.
yes,
But TCP does not go back to the last speed. He actually falls back to the originally agreed window size, which is this drops you're seeing. And then he starts building up. If 2 is going fine, he goes to 5, he goes to 8, and so on. Then again, at some point, it drops here, no acknowledgement. Again, he starts rebuilding. This is the way the irregular speeds which you sometimes see. That's the bandwidth optimization. Keeps increasing, trying to use the maximum possible bandwidth available to it. So it's an optimization method which TCP uses. Okay, so far?
Yes.
Good. What say we take a break and come back? There's one more function we need
Oh,
to finish before we can go into the next layer.
okay.
All right. 5 minutes?
All right. Okay.
Hello.
Yes.
Yes.
All right, great. So, any questions so far?
No.
Now we will go to the final difference. Rather, it's not a next one is not a difference because that's something that both of them commonly does. Though it is the major functionality at this layer. So again, this is something that is both of them don't do. Now the next one is called protocol multiplexing. That is something both of them do. What do you mean by multiplexing? I mean, if you learn signaling technology, that would normally mean combining multiple signals and transmitting them together, right? At the same time.
Yes.
Okay. So think about this scenario. Let's say you are browsing the internet, right? That is your screen right there. You have the Google server here. Now you might open up a window here, go to Google and search for CCNA. You might open up another window here and say go searching for say tourism. You could have a third window here and you might search for what? I don't know, atomic energy, whatever, right? We all do this, right?
Yes.
And maybe you have opened your Microsoft Outlook and you are doing a send receive of your mails here. Now your machine will have some sort of address on the internet. Your machine needs some sort of an address to get onto the internet, right? Namely the IP address.
Yes. Yes.
Yes.
Okay, so your entire machine has got one address and Google has got its own address. So when this request goes to Google, what is the source and destination address of this packet? Source will be ABCD, the from address, and the destination will be Google.
Yes.
What about the second packet? Same. What about the third and the fourth packet?
Same.
The same. Fine. So far, so good. Now, what happens when Google replies back to you? So now this is Google's reply packet. What would be the source? The source would be
Google.
Google's address, and the destination would be ABCD.
TCP.
which all of them same, right? That the source and destination addresses get swapped when the reply is coming back to you.
Yes.
All right. Now, when this replies comes back to your machine, all four of them, how does your machine make sure that the right answer goes to the right window? There are four different requests, right? All with the same source address and the same destination address. Or we don't even care if it's the same destination address. When the replies comes back, if they come to the same address, how would your machine keep track of which window generated which query? Are you understanding the problem here?
Yes.
What is the solution? I mean, forget networking. What would be the logical solution?
To assign a unique ID.
To each
So
window, right?
yes.
Exactly. So what we're saying is that this particular address is not enough. We need something more to identify each TCP stream or each UDP stream, correct? So that when the reply comes back, it can be sent back to the corresponding window, the one which generated that request in the first place, right? This is where
Yes.
both TCP and UDP use something called port numbers.
Yep.
Yeah. Now, both of them are capable of sending and receiving simultaneously on roughly 65,536 channels. So, port numbers can be compared to channels, just like your TV stations. I mean, your cable connection at your end, how many channels you must be getting? 400, 500 channels at a minimum,
Yeah.
right?
Yes.
But do you need 400 TVs to see all these channels? You don't, right?
No.
You just tune into different channels or frequencies, correct? Similarly, your TCP and UDP can transmit and receive on 65,536 different channels or port numbers. So what is done here is, once such a scenario comes, a port number is assigned. Now again, when you talk about port numbers, there are different levels of it. Port numbers 1 to 1023 are called well-known ports. Meaning typically we spoke about some protocols, right? HTTP, HTTPS, SMTP, POP3, FTP, and all those.
Yes.
Okay, all these protocols have got assigned port numbers, which are predetermined. So, for example, HTTP uses 80, HTTPS uses port number 443, SMTP is port number 25, POP3 uses 110, FTP uses 20 and 21. So, these are assigned, pre-assigned. So the first 1024 port numbers are called well-known ports and they are used by protocols, so you cannot use them for anything else. All right.
Yes.
Again, sir?
The port numbers, the first 1024 port numbers are pre-assigned to protocols, which means you cannot use them
Okay.
for any other functionality.
So these are only for protocols.
Exactly. And they are called the well-known ports, 1 to 1023. Right?
Protocols like HTTP, HTTPS, SMTP, POP3, something like these.
Yeah, which is why I put those port numbers there. If you look at it, all of them fall in this range, right?
Yes.
So now 1024 to something like 45,000 change, they are called registered ports, which means certain applications and certain companies have requested them and reserved for their own use. So basically, those also cannot be used for any other purpose. They are reserved for those particular applications or application players who have been registered there, which leaves us with the higher range of 45K to 65K. Out of the 65,000, first 1024 are well known and reserved for protocols. 1024 to 45,000 change is reserved for as registered for certain applications. What we have left is the 45,000 range to the 65,000 range, and these are called dynamic ports, which means anybody can use them for any purpose. Are you getting the picture?
Yes.
So now what happens is, when an application generates a TCP stream or a UDP stream, what your transport layer does is it assigns let's say 49,500 and 49,501, 49,502, 49,503. And when the original request is going out, the source now includes the port number also. So that will be ABCD colon 49,500. Destination, of course, will be Google. And again, let me ask you a question. With what is on the screen, what do you think would be the destination port for this request?
80.
Why? I mean, that is the
Uh,
perfect answer, but why?
Means you will be getting response on the form of HTTP. Sorry,
Exactly.
means HTML form. So it respond back with the hypertext
Exactly.
protocol.
Because we
So
have opened a browser, and browser is supposed to use either HTTP or HTTPS, right? So which means
yeah,
we are sending it to an HTTP protocol. So yes, the destination protocol would be 80, because on Google, HTTP listens on port number 80
80.
or 443, which is HTTPS, whichever it is. So you can send it either to 80 or 443. Got it? Now when Google replies back, what happens? So the source will be now Google at port 80,
Yes.
and the destination would be ABCD colon 49,500. When
Yes.
this reply comes back to this machine, do you think the machine will have any problem in sending it to the right window? Because that has been assigned already. Getting the picture there?
Yes.
Now, this is how multiple requests are not mixed up, and this is something that both TCP and UDP can do. This is one of the major features of transport layer, and this is the primary function of transport layer. As they what they say is application separation. Each application's traffic can be kept separate at the transport layer, and that is what primarily transport layer does. So going back, any question on this six functionalities?
No.
Okay, now I'll take Fais's
No.
the original question which Faiz asked. Can I have that question, guys? I mean, looking at this, what is the question that comes to your mind?
No question.
Come on, guys. The obvious question is, if TCP is so great and UDP is such a useless guy, why the hell do we need UDP still, right? That would be the obvious question, right?
Yes.
Since both of them seem to be doing the same thing, but TCP seems to be doing a great job of it and UDP seems to be mucking around. That's the obvious question you should be asking. I think Faiz asked me this in the beginning, right, Faiz?
Yes.
In a way, you asked me this question. See, the answer here is, what do you think is the answer? If both of them are still there, both of them does the same thing, TCP in such a seemingly great way, why do we still use UDP?
I don't know.
See, TCP, there are certain scenarios in which we use UDP exactly because TCP is so great. Meaning, TCP does so many things for each packet, right?
Mhm.
Make sure there's a connection, it makes sure there's reliability, sequencing, windowing, bandwidth optimization, blah, 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 the whole thing. Because it's doing all these things, it is slightly slower. Since UDP does not have to worry about all these things, comparatively it is lightning fast, right? So where perfection is the requirement, you would use TCP. Where perfection is not the requirement but speed is the requirement, UDP would be used. Now, if I'm sending you a blueprint of some design, what is important to you, the speed or the perfection of it, guys?
Perfection.
The perfection, obviously, right? You don't mind if it comes to you 5 seconds later.
Hmm.
Yeah.
It should be in perfect
Exactly.
condition.
So most of the protocols, HTTP, SMTP, FTP, they all use TCP, because for those guys it is not the lightning speed that is important, it is the perfection of data. But on the other hand, like what we are doing now, what is important when I am conversing with you, that when I say hello now, you better hear hello there, right?
Yes.
Mhm.
Which means we need speed there. Reliability is not a concern, because I say something, you don't get it properly, you will ask me, Vincent, can you repeat that, right?
Yes.
So this is where audio voice over IP is concerned, where video streaming over the net is concerned, those guys use UDP. Where they don't not concerned really with the perfection of data, but the speed or the instantaneous transmission is concerned. Clear?
Yes.
So which is why UDP is still around, where we don't need perfection, or where it is not a long stream of data. For example, something like a DNS query. Remember we discussed DNS query?
Mhm.
Resolving the name to an IP address.
Yes.
What is it? It's not a long conversation, right? It's one query sent. What does Google mean? And one reply saying it means so and so IP address, right? So DNS is another instance where UDP is used. All right, so far?
Sir, what was what do you say? It's still part of UDP?
You mean what applications uses UDP?
Yes.
As I said, namely voice over IP, audio traffic, right?
Uh-huh.
Um say
Hmm.
something like video streaming,
Uh-huh.
live video streaming, things like
Got
DNS queries, the domain name service queries. You remember the DNS we discussed yesterday?
it.
So such things basically use UDP, because for them it is not a long conversation, nor is it perfection of this thing. It is the speed that matters there. So those cases UDP is preferred, while others mostly prefer TCP. So other than these few things like your voice over IP, or live video streaming over the net, or DNS, other than these few, most of the applications would tend to use TCP. Whether it is your browsing, HTTP, HTTPS, whether it's you're sending a mail, your FTP protocol, all those are TCP. They use TCP. Again, it depends on the application developer, what protocol they want to be used, right? So we know that the upper
Yes.
layer protocols will depend on this. So HTTP will automatically go for TCP. Voice transmissions will automatically go for UDP. And this is the reason why it does that. So clear up to layer 4?
Yes.
Yes.
Okay. So tomorrow we will start with layer 3, and that will
Network
be
layer.
the network layer. And this is where we are going to spend quite some time there, because here we are going to understand the functions of the network layer, the protocols which functions there, and we are going to learn IP addressing, we're going to learn subnetting, That's where we're going to spend about 2 to 3 days. Then we spent a brief like half an hour on data link layer, and we briefly talk about the physical layer, and that would probably conclude your pre CCNA topics,
Okay.
right? So after which we can start on CCNA stuff, where we do basic device access. Now on that one day,
No.
I want to change the class timings. When I'm doing basic device access, right, I want to change the class timings because I need to have the lab for you, right? The physical machine, the physical equipment with me, right? So one day is, would it be okay for you to do your class in the morning?
Yes,
No.
Hello,
I can do.
don't say no. I'm getting up at 6:30 every day for you. So one day you get up at 6:30 for me.
Yeah, I mean, there's no problem to wake up early, sir.
Mm-hmm.
It's just means I have to get ready to go job.
Mm-hmm.
Means I I will may I can wake up at 5
Mm-hmm.
and we can conduct the class from 5 to 6 or 5 to 6:30 max.
Or maybe we can do it on a weekend
Yes.
because I don't want to carry all that equipment home here. It's not possible. I mean, one device, but I don't want to carry it around. With one single device, I can show you how it is accessed and how to start the initial configuration and all. But that I need to do it at the office. Normally, I don't take
Yeah.
classes from home, right? Mainly because of the bandwidth issues and all that. I normally do, but then since your timings are very odd, this is the first class of this time I do. I never do a class before 7:30 in the morning.
Oh, okay.
So I reach the office by 7:30, and I do a class and then continue with the office stuff. That's what I used to normally do.
Okay.
Mhm.
Yeah, it means I don't have any problem to wake up early, but if it's possible, means I can wake up at 4:30 also.
No, no. What we'll do is we'll try to do it over a weekend then. Yeah,
Okay.
that
Yes.
should solve the problem. All right then. You guys have a good night, I guess. Right?
Yep.
I'm going to go
All
kickstart my
right.
day.
All right. Yes. Have a good day, sir. Happy Diwali.
Oh, to
Okay,
you too,
sir.
guys. To you too. Bye.
Thank you.
Yeah.
Thank you. Bye.